Locus is actually a very easiest topic, very conceptual topic. But the thing is, if you refer any textbook or some online resources, it will be quite difficult to follow because many people do not explain why do we need root locus. Okay, why do we need root locus and what is it about? So that is one lack I have found on many resources. But some good textbooks have given explanation of 4 to 5 pages before starting the algorithm. So let me brief it here. What is root locus? So I have drawn a block diagram here. I have drawn a block diagram here, and I have included all the terminologies which we are already familiar with. So R of S, everyone knows, C of S, H of S, everyone knows. And here in the forward part of the block diagram, I have called one additional terminology called K and G dash. Just for the sake of understanding, I have defined them separately, but together it is called as G of S, which we already know. So G dash is nothing but plant transfer function. So G dash is called a plant transfer function. You can imagine it as our bicycle. So bicycle is one of the plant. Okay, one of the plant. Then what I mean to say plant in detail is that when you operate a plant, your objective is obviously to control it. For example, if you take your bicycle as a plant and if you operate it, I mean if you start riding it, your first objective is to control the bicycle and then to reach the destination. Fine. So without controlling bicycle, you cannot reach the destination. What I mean to control the bicycle is that you should ride it very smoothly. Okay. Should ride it very smoothly and reach your destination. That is your control objective. So riding on two wheels is what I can say as controlled plant. Controlled plant. So obviously one cannot ride a bicycle. Okay. What I should say, one cannot ride on single wheel up to your destination. If you can ride it with one wheel, then you have a very good control strategy in your brain. So what we call as a wheeling. Okay, wheeling. So that is one good control. I mean, advanced control we can say. But one cannot ride bicycle by dragging it on the ground. Okay. So by dragging it on the ground, that means you cannot or you are not able to control the bicycle. That's why you are just dragging it on the ground. So that is another scenario of uncontrollable strategy. But for time being, keep in mind that G dash is a bicycle plant transfer function. And with addition to that, I have defined a K, which means you can take your pedaling speed as a gain factor or system gain. Fine. So if you start operating your plant, obviously the speed of your bicycle will vary. So it will vary depending on the situation, on the road condition, we can say. So when you encounter different road conditions, obviously your pedaling speed or pedaling effect will change accordingly. Okay, sometimes you apply a brake, sometimes you ride without pedaling. Okay. So this gain has something to do with bicycle. Something to do with bicycle. So which for time being I consider it as a speed. Okay, speed or speeding element, which is nothing but an accelerator. Okay, speed or speeding element. So now what we have to understand is for a bicycle, what is the range of operation of K, or how much you can accelerate to run it properly, or what is the maximum speed you can run to control it properly. Fine. So while we operate the system, we are sure that this K is not going to be a constant value or a fixed value. It will vary. Fine. It will vary when we operate. So that's why I call it as a variable. So variable has a different interpretation also, but for this example, while we operate the bicycle, our gain is obviously, our speed is not obviously going to be constant throughout the operation. So is that is clear for everyone? So this is how plant transfer function and the system gain are related. Related. If suppose I remove K in this block and just mention only G dash, It is a closed loop transfer function for operating a bicycle. Okay, and it gives a meaning that there is no gain term in the system, so it operates at very constant speed, no variation at all, and that is not possible practical. Practically, we can never operate any plant or system with a constant, say speed is just a one parameter. We can never operate any system or plant with a constant variation, say a constant speed. Therefore, adding k in the block diagram gives a meaning that the dynamics of the system varies according to the situation, according to the environmental condition. Okay, so this k can be varied either manually or automatically. That is the next stage. That is the next stage. Okay, suppose if you imagine a self-driving bicycle where you just have to sit on the bicycle and it will make every decision on itself. So that is a scenario of automatic variation of speed. But there exists a k in the overall transfer function. So manual means you are doing it manually. Okay, so this is about k system gain. This is about system gain k. So if you have a brain, and I will define the transfer function by g dash. And if I give a gain factor k to it, your operation of brain obviously depends on surroundings environmental conditions. Then gain k will change accordingly. Okay, so therefore the g of s or the forward path transfer function will by default have k in every block diagram or in every plant. So whenever you write a transfer function for any system, now onwards we will include k along with that. So till now we have dealt with the analysis of control systems without k, and now onwards we will deal the analysis of control systems with k only. With k only. So what I'm going to do about this analysis with k is that I will check the first and foremost thing, I will check the stability of the system with variation in k. So how the stability is going to change with the variation of system gain. So again, come back to bicycle example. If you're riding your bicycle, say at 10 kilometers per hour, your gain k you can consider it to be say 10. Okay, k equal to 10. So at k equal to 10, you can control the bicycle very nicely without much difficulty. And with k equal to 0, which is equivalent to a speed of 0 kilometers per hour, it is as good as like you are trying to balance the bicycle on two wheels, which is quite difficult. Fine. So if you have tried balancing a bicycle, you know it. It is quite difficult. It's not like it will not last for longer duration. And at k equal to say 100 kilometer per hour, just an imagination, it will be very, very speed. Hmm? It will be very, very speed. It is as good as tying your bicycle with one Ferrari car with a rope and you are following it. Do you think it is easy to balance? No. If you just encounter a hump at that speed, now the next things are, I mean, not explainable. So at k equal to 100 is also it is difficult to control. At k equal to 0 is also it is difficult to control. But at k equal to 10 it is a very nicely controllable. Very nicely controllable. So now this explanation of different scenarios we have to put into mathematics. We have to put into mathematics, physics into mathematics. So suppose someone will come and ask you, okay, someone like who has understood engineering with very less knowledge and comes and asks you, you explain me why it is difficult to control the bicycle at 0 kilometer per hour with mathematics. Fine. So someone asks you some random question to explain that, then you really have to take that as a challenge and you have to explain with mathematics. That's where your concept and knowledge will come. Okay, if a layman comes and asks you why it is difficult to control it at 0 kilometers per hour, then you try, yeah, you will come to know. You try and then you will come to know it is difficult to control. That is a common answer, but as an engineer, you should take it as a challenge and put it in mathematics. Fine. So that's what we are going to do now. When it is difficult to control, when it is easy to control, why it is like that, what actually happens in the system dynamics, is that is what we are going to do now. Fine. So this topic is more or less, all right, okay, is dependent only on K only. Okay, you tell about the speed and you tell the customer your stability level. Okay, so it's more or less going to do with only the system gain K. Therefore, root locus is about the stability of the system or controllability of the system or behavior of the system with respect to K only. So let us make it clear before proceeding. Then H of S is obviously a feedback element, and it is most of the time it is unity. So why it is unity, I will make it clear again. Suppose you are riding a bicycle, your eyes will act as a sensor. Eyes will act as a sensor, and pedaling, your legs act as a actuator. Okay, actuator and sensor, you are already aware. Actuator means is something change, something like some kind of a valve, you can say, connected to a DC motor. So a DC motor, when it receives some signal, it rotates the valve. So we can call a simple DC motor as an actuator. Similarly, your legs, when imagined as a robotic leg, they are also nothing but a configuration of motors and chains. So your legs will act as an actuator, which will actuate when they receive some signal. Your eyes will sense and send a signal to legs. So this is sensor actuator configuration. And in most of the cases, it is unity. It is equal to 1. Why? Because as soon as your eyes sense something, there won't be any delay in actuating your leg. Fine? In actuating your leg or in actuating the brake through your hand. So that's why it is a zero delay signal transfer in the feedback path. In the feedback path. So whatever you see, immediately it is active. Fine. So that's why it is near to unity. Near to unity. But when you operate with a huge or complex system, such as say missile or rocket, so the sensor which is fixed on the head of the rocket or a missile will take 1 millisecond of time or 2 millisecond of time to pass that information to actuating system. Actuating system, which is like you can say fuel combustion chamber. The fuel combustion chamber has to decide on which direction it has to move based on the sensor sense which is kept on the head of the missile or rocket. Okay, so that element is called as a delay. I mean, sorry, the time taken to transfer that signal from the head to the combustion chamber is called as a delay in communication. So that delay will be put usually in the feedback path in complicated systems. So the delay is written in terms of Laplace transform, then it will be substituted here. It will be usually in terms of exponential time term, something like e raised to minus 2 milli s 2 into s, something like that. But we are not going to do that now, and we assume the feedback equal to unit. Fine. So the operation of this block is well known. You have already known what is closed loop diagram and what is the difference between open loop and closed loop. So now I hope I am clear with all the terms present in this block diagram. If anybody has any queries, you can ask. I can wait for a minute. Okay, yeah. Abhijit Sahu, any queries?
Sir, little bit doubt in K part, sir.
Yeah, you put your question.
Sir, like system gain, I'm not properly getting it. I understood the part where you are telling, like in the video where you referred to K different values, 0, infinity, and that part. But like I'm not fully, I can't imagine it, how you're talking about that. Like GS, HS, that parts I'm getting it properly. But K part, I'm a little unsure about. Can you?
Okay, see, now imagine car as a plant. Sahu, answer me parallelly.
Yes, sir, yes. Sir. Yeah.
You imagine a car. Okay, car is a system. It is as good as a mass block. You can imagine, right? Mass
Yes,
spring
sir.
damper. So if you model it, suppose imagine 1 divided by m square plus bs plus k. That is the transfer function.
Yes, sir.
Okay. But if I include k in that transfer function, it is k divided by ms square plus bs plus k.
Yeah.
So including k interprets or tells me that this system this system has some dynamics which depends on the speed.
Yes.
Removing k tells me that it is just as a standing car.
Okay.
So if I include k, like something like a speed element, then the dynamics depends on k means the dynamics of the car depends on the speed of the car. So obviously, if you have say riding car at 60 kilometer per hour and riding car at 500 kilometer per hour, there will be different dynamics, right, with two different speeds.
Yes, sir.
So you always feel while riding at 60 kilometer per hour, you can easily control if any object comes.
Yeah.
But while riding at 500, you feel that it is very difficult to control if I encounter any hump.
Yeah.
So my mathematics of including k in the transfer function gives me an idea that, hey designer, you be careful. There is some k, you need to take care. And you need to explain what is the limit for that k. Fine?
Okay.
So the analysis
Yeah.
goes on like this.
Yes, I got it.
So that's what system gain means. Okay.
Okay. Yeah.
System gain. It's usually referred different in different way in some other textbook, but let us keep it as system gain or plant gain, which is equal to k. And you just remember a bicycle example. That is more than enough. All numericals I will solve with the same thing. Okay. So you will get it very easily. Anybody else has any doubts?
Sir, but the definition of transfer function, it means that
Hmm.
taking into account
Hmm.
depending on the input, what will be the output?
No, Abdul Bakar, you are making the same mistake. Transfer function is not related to input output. It depends. It is only with respect to system dynamics.
Okay, sir.
You have a mass spring damper. Transfer function is 1 divided by ms square plus bs plus k. That is transfer function.
Yes, sir.
You apply any input, you check the output based on that relation. But where does k come in the transfer function is existence of k in the transfer function just gives you an idea that the transfer function has a different dynamics for different k. See, 1 divided by ms square plus bs plus k is not same as 10 divided by ms square plus bs plus k, right? Now k has changed to 10.
Yes, sir.
Yes.
Yes, sir.
So similarly, it will have a different transfer function when k is changing.
Okay,
So
sir.
it is
Got
as good as system parameter and related to system dynamics only.
Okay.
Earlier, I might have said that whenever you encountered a constant in the numerator as multiply by input and all, that was because I couldn't convince you about the system gain at that time. But now onwards, the definition will change.
Okay, sir. Got it.
Okay. Okay. So we'll move on to the next part. So everyone is aware that what is the transfer function, closed loop transfer function now. It is C of S by R of S. Numerator is this forward path transfer function k into g dash of s divided by 1 plus k into g dash of s into h of s. Okay, so the additional term k has been introduced both in numerator and denominator. If anyone does not know how to get this transfer function or how it has been derived, you please go through the previous videos without fail. This is a crucial part. Okay. But anybody who is regular to class and still not understood, you are welcome to ask your doubt. Okay, I don't deny to explain it once again. So this is our closed loop transfer function. Numerator is k into g of g dash of s divided by 1 plus k into g dash of s into h of s. So this transfer function has, okay, the denominator. So pardon me 1 second. Fine. So the next step is that stability of the system depends on obviously the denominator of closed loop transfer function. So the denominator of closed loop transfer function is nothing but 1 plus k into g dash of s into h of s. Fine. So the roots of this denominator will decide whether it is stable or unstable. Next is, let me take one example. Imagine this is a now transfer function of standing bicycle or plant g dash of s. I will give feedback equal to unity, and I will now define g of s equal to k into g dash of s, which is k into s plus 2 divided by s plus 3. And indirectly I am conveying a message that now the plant is operated with gain, or the dynamics of the plant depends on gain k, which is nothing but system gain we call. And h of s still remaining equal to unity. We get g of s into h of s, this multiplied with this equal to same as this. So this has a different definition now. We call g of s into h of s equal to the transfer function given by this as loop transfer function or open loop transfer function. So some textbooks refer as loop transfer function, some textbooks refer as open loop transfer function. But whenever I say like given g of s into h of s equal to like this, you should understand that it is the loop transfer function. So I hope I'm clear. So what we are going to do now is, let us see how does the closed loop roots or characteristic equation roots look like with this example. Fine. So g dash and k are replaced with g of s, h of s now. So the next one is rewriting. Okay, next one is rewriting this equations to find the characteristic equation. So we have c of s by r of s here. So g dash and k are gone and g of s has appeared here. So 1 plus g of s h of s is the denominator. So k into g dash is replaced by g of s. So let me write those transfer functions. So g of s is k into s plus 2 divided by s plus 3, and 1 plus g of s h of s is 1 plus k into s plus 2 divided by s plus 3 into 1.
Sir,
Yes.
we can see only the photos.
Sir.
One second. Oh, sorry. I'm sorry. Now you can see.
Yes, sir.
Okay, sorry for that. So this is a g of s, which is k into g dash of s, and this is our closed loop transfer function. So k into s plus 2 divided by s plus 3, 1 plus k into s plus 2 divided by s plus 3 into unity feedback 1. So this is equal to s plus 3 getting cancelled. We will have k into s plus 2 in the numerator, and s plus 3 is taken as a common. So s plus 3 plus k into s plus 2k. Simple algebra. Fine. So this is our overall transfer function now. So we have in the denominator s into k plus 1. I have just taken a common. Okay. S and ks are here. So I have taken s as common, k plus 1. Then I have kept 3 plus 2k as it is. 3 plus 2k as it is. So for stability, the roots of this denominator are important. So if the roots of this characteristic equation lies in the left half, we know that the system is stable. And if the roots of this characteristic equation lies in the right half, we know that system is unstable. But if the root lies on the imaginary line, the system is critically stable. So that's what we had studied. And now we have one new thing here, which is nothing but k. Okay. So k is putting us some constraint that I also will contribute for the location of poles. I also contribute for the location of poles. So that's what now roots are dependent on k. You cannot directly evaluate the roots, but you should ask what is a k, then only I can tell the roots. Then 1 plus g of h of s equal to 0 is our denominator characteristic equation. Therefore, we get s in, I'll directly consider only this part because numerator is irrelevant for us for stability. So I will take the characteristic equation s k plus 1 plus 3 plus 2k equal to 0. Then I will rearrange that how I will get the roots in terms of k. How I will get the roots in terms of k. So this is the simplest modification I can do. I will write s equal to in terms of k. Then I will go on substituting k values. Then I will go on getting the s values. It is as good as that. So what he will say, when k is 0, when speed is 0, my root is minus 3 minus 2 into 0 divided by 0 plus 1, which is equal to minus 3. So minus 3 lies in the left half of S plane. So you have designed some very nice bicycle that even if you don't ride it, you can easily balance or control or make it stable at k equal to 0. Okay, so imagine some cycle for which if 0 is the speed, the root of that bicycle lies in the left half of S plane at minus 3 and it is stable. You can easily control. Okay, I will go on increasing k now. So I'll make k equal to 1. So minus 3 minus 2 divided by 1 plus 1, it is minus 2.5. I will check what is the root at k equal to 10. So minus 3 minus 20, 10 plus 1. So 10 means minus 2.09. So the root is still minus 2.09. I will check if my bicycle I can ride at infinite speed. What is the root? So at infinity you have to make a modified calculation. So we have minus 3 minus 2k divided by k plus 1. So at infinity you have to take k as common. Take k as common, it becomes minus 3 by k minus 2, 1 plus 1 by k minus 2. So therefore you have s equal to minus 2. Fine. So 1 divided by infinity will get 0. So what we are observing, you can ride your bicycle at any speed, all the roots will lie in the left half only. Oh, very nice bicycle you have. Fine, some imaginary bicycle. So these points on the S plane, when they are drawn for a respective k, when you are drawing these points on the S plane, they obviously form a locus. Okay, so locus of roots we say. We add one additional term, which is locus of roots. So locus of roots is obviously obtained by one varying parameter, and that is k here. Therefore, that is called as root locus. That is called as a root locus, and this is how it looks like. You have a S plane here, real axis, imaginary axis, sigma j omega. Then you have a minus 1 point here. This is not cross, sorry for that. This is minus 1 and it is minus 2. What is minus 2? Minus 2 is 0 of the system. 0 of the plant. And we have a minus 3, which is pole of the plant. And here we have a locus of points. Let me denote them one by one. 1, 2, 3. Starts with minus 3, goes something like this, and finally at infinity we have at minus 2, and it starts at k equal to 0 from minus 3. This is locus of roots. Okay, this is locus of roots. If suppose there would have not been any k term, then we couldn't draw this locus. That's it. So how it looks in the next level? So it is called as root locus for g of s h of s. So this is g of s of s, and this is real axis, imaginary axis, s plane, sigma plus j omega, and we draw a root locus on the line on which the roots are changing. So roots are changing something like minus 3, minus 2.5, minus 2.09, finally at minus 2. So this is root locus. Fine. So root locus, one conclusion from this root locus is that it started at k equal to 0 from minus 3, which is pole of the plant, and ended at minus 2, which is 0 of the plant. 0 of the plant. So one conclusion is root locus starts from the open loop pole, and ends at open loop 0. This open loop, closed loop are quite confusing as of now, but when we get accustomed with that, you will understand. Let me proceed quickly. Since we are considering 1 plus g of s h of s, which is closed loop characteristic equation or characteristic equation, just characteristic equation, we can get the information on how closed loop poles or characteristic roots behave with respect to k. So there is a key point here. The question given was only plot the root locus for g of s h of s. Fine. But we have plotted for this equation. We have plotted, rearranged s equal to something and then plotted. So what essentially it means is we are taking the open loop information and putting it into a closed loop analysis. analysis, and we are then drawing the locus with respect to k. Fine. So therefore, what we can conclude from this is root locus tells us about the variation of characteristic equation roots or closed loop poles on S plane with respect to k from given loop transfer function. So we know given open loop transfer function, but we are plotting the locus for closed loop roots. Okay, this is something like beauty of mathematics or surprising. We know open loop and we are evaluating the stability of closed loop. So that's what final conclusion. So therefore, what conclusion, final conclusion we can make is stability of the system. Who is having, which is the next class? Guys, next class is there?
Elective, sir.
Elective, you can join 5-10 minutes late, no? 5 minutes at least.
And for DR, it's the same link, sir. And
Oh.
for other one, we have to go to other link.
Okay, I'll quickly finish off. So we have stability conclusion now. We have asymptotic stability. If the complete root locus lies in the left half of S-plane for all k equal to 0 to infinity, then the system is asymptotically stable. Then we have conditional stability. If the part of the root locus lies in the left half of S-plane and part of the root locus lies in the right half of S-plane, the system is stable only for certain range of k, but not for k equal to 0 to infinity. Fine. So this is one such example. This is having a 0 at plus 2, pole at -3. And if you plot the root locus, you will definitely get this line. Okay. So what conclusion we can make is for some k values, our root is moving to right half, which means above certain speed of the bicycle, there is instability in the bicycle. But for certain range of the bicycle, say from k equal to 0 to 100 km/h, your bicycle is stable. Above that, it is unstable. So that's what the conclusion. We'll do it in the next class. Thank you.